Hey guys, I just wanted to step in here and give you a little crash course on separable differential equations. These come up all the time in the theory of differential equations. It's probably the first and most standard type of equation that everybody should learn how to solve. The thing of it is, if you know how to do integration and you know how to do elementary high school algebra, you can solve separable differential equations. So one of the biggest challenges with the separable differential equation is just recognizing that something is separable. I put the definition here on the board. A first order differential equation is separable if it can be written in this kind of a form. Some function of y times dy dx equals some function of x. And of course you can rearrange that, and when you put the y terms on the left side and the x terms on the right side, you really see why it's called a separable differential equation. You have separated the x's and the y's onto the two different sides of the equal sign. Now, the thing that can be difficult, as I said, is recognizing a separable differential equation. And that's because it's not always given to you in an already separated form. Sometimes you have to do some algebra to manipulate the equation that you were given in the first place so that you can get it separated. And sometimes you can try to do that and it just doesn't work. So I've seen people try to take a differential equation that's not separable and get it separated, and of course it's not necessarily going to work. But once you get it separated, all you have to do here to solve it is integrate both sides. And then, if possible, you can even solve explicitly for y. So I'll just add that. That's sometimes not possible, but if possible, you can try to explicitly solve for the unknown function, which is, of course, the goal of differential equations, solving for the unknown function y of x. Okay? So with that little background, that's really all there is to the theory of this. We can just maybe do a couple of examples. So here's an example. Let's suppose we want to solve y prime equals y squared over x squared plus 1. Okay? Now, it looks like I can take the y's and get them separated from the x's here. To help myself out with this, it's sometimes a good idea to rewrite the prime notation of derivatives using the dy dx, just because you're going to be splitting those differentials onto opposite sides of the equation anyway. So if I do that, it would look like this. So here's my differential equation, and in this case, it's pretty easy to separate it, right? All I have to do is pull the y squared underneath the dy and put the dx up on top of the x squared plus 1. So again, this is the algebra. In this case, the algebra is very simple. It's not always quite this simple, but you do a little bit of algebra and you get it separated. Okay, next thing is we just integrate on both sides. So we're going to integrate on the left side. When we use the power rule on y to the negative 2, we're going to get negative 1 over y. And it's a pretty standard integral from earlier in calculus. The antiderivative of 1 over x squared plus 1 is the arctangent of x. And of course, we have to have a plus c. Technically, we have a plus c on both sides of the equal sign here, but I'm going to lump my constants together and call them a single constant, a new constant, which is just c right here on the right-hand side. Okay, great. So with that, we have already performed the integration, and now, if possible, we'll solve for y of x. In this case, that's very easy to do. We just have to take reciprocals and throw in a minus sign. So the final answer would just be y of x equals negative 1 over the arctangent of x plus c. And again, if we had been given initial conditions, we could solve for c. That's for an initial value problem. But if I just want the general solution, this is the general solution to the differential equation, it's going to have that C as part of the answer. Okay, let's try one more that's maybe a little more involved than the first one. This one was very straightforward to separate the variables. Okay, so let's try a second example here. Let me write it down for you. 1 minus x squared times y prime, and then plus xy equals 4x. And this time, I'm going to attach an initial condition. Now, if you have an initial condition, you don't need to use that initial condition until the very end of the problem. So we're going to set aside the initial condition for now and focus on just solving the differential equation. This time, when you look at this equation, it may not look quite so obvious that it is separable. But what you can do, in addition to rewriting y prime as dy over dx, what you can do is you can subtract the xy to the right side and then factor an x. See, there's an x in both of these terms, and you can factor it here, and that allows you to put the x's and y's in different factors, which is often how you're going to be able to get the equation separated. Okay, so with all of these factors as such, with no x's or y's mixed, now we can pretty easily separate it again. I'm going to just move the 4 minus y underneath the dy, and I'm going to put the 1 minus x squared underneath the x and the dx. So there you go. Actually, to make the integration slightly simpler, it's not an absolute requirement that you would do this, but in this case, it's a little easier if you just negate both sides, both denominators on both sides of the equation. So I replaced 4 minus y with y minus 4 on the left side, and on the right side I replaced 1 minus x squared with x squared minus 1. So I did the same thing to both sides of the equation. Okay, so now let me come up here and integrate both sides. The integral of 1 over y minus 4, if you just use a little u substitution, you can let u equal y minus 4, and then the integral of 1 over u is just the ln of u. So this will be the ln, and it should be absolute value of u. So the absolute value of y minus 4 on the left side. The right side can also be solved with a u substitution. I need to put a 2 on top because if I let u equal x squared minus 1, the derivative of that would be 2x. And so I can put a 2 there, but I have to pay a price and put a 1/2 out in front. And it's that 1/2 that you're going to see right here. So we have a 1/2, and then again, what's left here now is just du over u. And we can just take an ln to get the antiderivative. So it's going to look something like that. And again, I'm going to put my plus c on the right-hand side. So a couple of u substitutions to integrate the left side and the right side. And this is what we end up with. This is an implicit expression that relates x and y, but we can actually solve this one for y as well. It's a little more complicated, but if I exponentiate on both sides, I can cancel the ln. So I'm just going to raise both sides to the e. That's usually the best way of getting rid of a natural logarithm, is to exponentiate it. Now on the right side I have e to a pretty big exponent here. There's a plus sign between two parts to this exponent, and if you remember your laws of exponential functions, I can write this as e to the first part times e to the second part. E to the second part, that's just e to the c. I'm just going to call that c1. It's also a constant, it's just not the same constant that we started with. And then the first term here would look like that. So c1 is just e to the c. And it's good to change the symbol for your notation there so that we know that the constant is possibly going to be changing. But there's still a constant here, it's called c1. Now I would like to cancel my e and ln right here. but the 1/2 is kind of in the way. So what we can do to handle that is, you may remember that you can take a coefficient in front of a logarithm and put it up as an exponent. So in this case, the exponent would be the 1/2 power, and so that's just a square root. So now the e and the ln have a clear path to each other. We can cancel them out, and this is what we'll be left with. Okay. Now, we're not done. This is the absolute value of y minus 4. I can remove absolute value bars, but it does cost me a plus or minus sign. And plus or minus of C1 is actually just another constant, so I'm going to call it C2, like that. So when you say plus or minus C1, it could be plus C1 or it could be minus C1. We don't know which is the solution that we're looking for. But if we just put a generic constant, which I'll call C2, in front of that, it handles both scenarios. Okay? And so we can now solve for y by adding 4 to the right-hand side. Okay, I hope this is all making sense. You know, if it's not, of course, you're welcome to pause and rewind and watch this again. Or, better yet, just ask me to explain any steps here that maybe you're not comfortable with. And I'll be happy to do that. We're not done, are we? I almost forgot. We have an initial condition. So I have to go back and put in the initial condition. Let me do that right here. We know that when x is 0, y should be 8. So if we plug that in, I'm going to put in an 8 for the y. 4 plus C2 times the square root of, well, this is 0 minus 1 with an absolute value bar on it. That's just 1. Okay, so C2 is equal to 4. And so finally now we can plug that in. 4 plus 4 radical absolute x squared minus 1. There's your final answer. Okay, I hope that makes good sense. That's a particular solution. Remember, when you've plugged the generic constant in that was part of the general solution, with a particular number, you get the particular solution. So, general solution versus particular solution. Okay. One last thing, and then we'll call it good. Newton's law of cooling. I had mentioned that as a nice application of differential equations. And I just want to point out, call this example 3, I just want to point out that this differential equation is in fact separable. Instead of x's and y's, this equation is in terms of little t, which is time, and big T, which is temperature of the object. The other expressions that you see, the other notations, are just constants, right? K is a constant of proportionality. T sub m is the temperature of the room. Well, this is actually already very easy to separate. I can put all of the big T's on the left side and all of the little t's on the right side. It doesn't matter which side you put the K on. I'm just going to leave it on the right side. It's just as easy to do that. But that is the separated form of Newton's law of cooling. And it's very similar to the previous example that we just did. When we integrate on the left, we're going to get a logarithm. On the right, when we integrate a constant, we just get that constant times t plus c. Of course, we have to always include that. Okay, we exponentiate again. And that gets rid of the logarithm on the left side. And on the right side, we have e to the negative kt plus c. E to the c is c1, e to the negative kt. We take off our absolute value bars. That costs me a plus or minus sign. I'm going to absorb that into a C2. And I can now solve for the temperature of the object. T sub m plus C2 e to the negative kt. There it is. That's the answer. That's the formula for the temperature of an object at any time t. notice that as t goes to infinity, this is a negative exponential. It's going to go to 0. So as t goes to infinity, this term on the right becomes very negligible, and the temperature of your object approaches the temperature of the room. Exactly what you would expect. And it does so in this exponential pattern, exponential manner. All right, those are some examples of separable differential equations. I hope that it's helpful. I actually have another video with applications of this Newton's law of cooling in it, where you actually use this formula to solve a word problem. So you can take a look at that if you like. I have a link for that available as well. But this is the nuts and bolts of the procedure of solving separable differential equations. Thanks so much for watching, guys. I'll see you soon.